Hi there. Welcome to Physics at Fire. Today we are going to have some numericals based on those topics that we have covered till now. So, let's start. Formula that we are going to use are Q is equal to NE, and mass transferred during charging is ME into N. Let's move towards the first numerical. If a body gives out 10 raised to power 9 electrons every second, how much time is required to get a total charge of 1 coulomb from it? Please have a pause and try it yourself, or just continue. Number of electrons given out by the body in 1 second is equals to 10 to the 9th. Charge Q, given out by the body in 1 second, is equals to NE, that is equals to 10 raised to power 9 into 1.6 into 10 raised to power minus 19 coulomb, which is equals to 1.6 into 10 raised to power minus 10 coulomb. Now, time required to get a charge of 1.6 into 10 raised to power minus 10 coulomb is equals to 1 second. Now, time required to get a charge of 1 coulomb is equal to 1 by 1.6 into 10 raised to power minus 10, that is equal to 6.25 into 10 raised to power 9 seconds, which is 6.25 into 10 raised to power 9 by 365 into 24 into 3,600 years, in which we will get 198.18 years. Thus, from a body emitting 10 raised to power 9 electrons per second, it will take about 200 years to get a charge of 1 coulomb from the body. This shows how large is 1 coulomb as the unit of charge. Now, let's move to question 2. How much positive and negative charge is there in a cup of water? Please have a pause and try it yourself, or just continue. Suppose the mass of water contained in a cup is 180 grams. We are taking 180 for the sake of convenience only. And the molecular mass of water is 18 grams. Number of molecules present in 18 grams of water is equals to Avogadro's number, that is 6.02 into 10 raised to power 23. Therefore, number of molecules present in a cup of water is N is equals to 6.02 into 10 raised to power 23 into 180 by 18 is equal to 6.02 into 10 raised to power 24. Each molecule of water contains 10 electrons as well as 10 protons. And total number of electrons or protons present in a cup of water is N dash is equal to N into 10 equals 6.02 into 10 raised to power 25. Hence, total negative charge carried by electrons, or total positive charge carried by protons in a cup of water is Q is equal to N dash E is equals to 6.02 into 10 raised to power 25, into 1.6 into 10 raised to power minus 19 coulomb, which is equals to 9.632 into 10 raised to power 6 coulomb. Let's move to question 3. Calculate the charge on an alpha particle. Given charge on a proton is equal to plus 1.6 into 10 raised to power minus 19 coulomb. We know that an alpha particle contains 2 protons and 2 neutrons. Therefore, Q is equal to plus 2e, so it will be equal to 3.2 into 10 raised to power minus 19 coulomb. Now, let's move to other problems, and the formulas that we are going to use in that are F is equals to K, Q1 Q2 by R square. Now, let's move to question 1. A free pith ball A of 8 grams carries a positive charge of 5 into 10 raised to power minus 8 coulomb. What must be the nature and magnitude of charge that should be given to second pith ball B fixed 5 centimeters below the former ball so that the upper ball is stationary? The pith ball B must be positive, that is, of same nature as that of A, so that the upward force of repulsion balances the weight of pith ball A. When the pith ball A remains stationary, F is equal to m1 into g, or 1 by 4 pi epsilon naught, into Q1 Q2 by R square, that is equal to m1 into g. But m1 is equal to 8 grams, that is equal to 8 into 10 raised to power minus 3 kg. Q1 is equal to 5 into 10 raised to power minus 8 coulomb. R is equal to 5 centimeters, that is equal to 0.05 meter. Therefore, 9 into 10 raised to power 9 into 5 into 10 raised to power minus 8 into Q2, by 0.05 square will be equal to 8 into 10 raised to power minus 3 into 9.8. So, Q2 is equal to 8 into 9.8 into 0.05 square into 10 raised to power minus 4 by 9 into 5 is equals to 4.36 into 10 raised to power minus 7 coulombs. Let's have another example. Two identical charges, Q each, are kept at a distance r from each other. A third charge Q is placed on the line joining the above two charges such that all the three charges are in equilibrium. What is the magnitude, sign, and position of the charge Q? Suppose the three charges be placed in the manner that the charge Q will be in equilibrium if the forces exerted on it by the charges at A and C are equal and opposite. So, K, capital Q, small q, by x square will be equal to K, capital Q, small q, by r minus x square. So, we get x square is equal to r minus x whole square. Therefore, x is equals to r minus x. Hence, x is equal to r by 2. Since the charge at A is repelled by the similar charge at C, so it will be in equilibrium if it is attracted by the charge Q at B, that is, the sign of charge Q should be opposite to that of charge Q. Therefore, force of repulsion between charges at A and C is equal to force of attraction between charges at A and B. Therefore, K, capital Q, small q, by r by 2 square, will be equal to K, capital Q, by r square. Hence, we will get the value of small q is equal to capital Q, by 4. Let's have one more example. Two identical metallic spheres, having unequal, opposite charges are placed at a distance 0.90 meter apart in air. After bringing them in contact with each other, they are again placed at the same distance apart. Now, the force of repulsion between them is 0.025 newtons. Calculate the final charge on each of them. The two spheres will share the final charge equally. Let Q be the charge on each sphere. F is equal to K, Q1, Q2 by r square, that is, equal to 0.025 newtons. That is, 9 into 10 raised to power 9, into Q by 0.90 square, is equal to 0.025. Therefore, Q square is equal to 0.025 into 0.90 square by 9 into 10 raised to power 9, which is equal to 225 into 10 raised to power minus 14. Hence, Q is equal to 1.5 into 10 raised to power minus 9 coulomb. That's all about that numericals. We will have some important numericals based on superposition principle in further videos. Thank you for being here. Stay tuned, and don't forget to like, share, and subscribe, Physics at Fire.